Okay, I have chosen a topic that with no recent results. In fact, with not many past results either. I will, except in classical cases, which I will describe. I imagine that almost nobody here is familiar with the topic. I'm sorry if I insult some of you, but I think the risk is small. Let me introduce right away the notation and basic definitions. Yeah, except I don't see them, but so the only thing really important is the boldface V. So in each plane to the manifold, it's a C-infinity manifold. C-infinity of UV are the section of that thing. It's really, we have a bunch of vector fields with smooth coefficients, smooth vector fields, and they have certain properties which are coming. There are two important things there. V itself, so you have this smooth family of subspaces of the tangent space, but it's complexified. So the vector field will be complex. The important other thing is the orthogonal. And that's orthogonal in the sense of vectors and covectors. So the orthogonal is in the complexified cotangent bundle. Characteristic V for people in PDE, it's a standard thing. You take all the vector field, they have symbols. That means instead of partial derivative, you put the frequency. Is there chalk? Yeah. Okay, so we have locally coordinates. And the dimension is n of the manifold, or maybe not n, capital N. And instead of that, the symbol is this. You put the frequency. And you take all the sections of the capital V, the boldface V, the subbundle, and they all vanish on a certain subset of the cotangent bundle, which is phase space, in phase space XC, and that's a common zero. Okay, here it's a new terminology. If a function or a distribution of, or even more generalized thing satisfies the homogeneous equation for all the vector field over an open subset, I call it a solution. That's what it means. Okay. Mainly there would be definition. I'm not going to give anything technical. And the theorem would be stated without proofs, and there's not much of it. Okay, we come now. Wait. Okay, here is the main definition. The structure, that's V. V is the structure of bundle set. Is involutive if the Lie bracket of two smooth sections is a smooth section of V. Okay, that's involutive. We are very familiar when V is real, in the all real, because that's the basis for the Frobenius theorem. But here it's complex. Locally integrable is a stronger notion. It means that locally, the orthogonal is generated by exact one forms, which of course are, because of the Poincaré lemma, are the differential of some function, smooth function. That's a strong hypothesis. Without that, I cannot say anything. Okay, and involutive does not entail locally integrable. Let me say a word for that, a very quick word. Nirenberg gave an example in the late 70s of one vector field in R3, in tree space, which has the property defined globally, C-infinity coefficient. has the property that you take any open set, anywhere, as small as you wish, the only solutions, so solution of the homogeneous equation, are the constant. Okay, that seems to be a really sick kind of example. Then Jakubowicz and I prove, I'm talking about classical solution, C1. Jakubowicz and us, we prove rather easily that most vector fields in 3 variables have that property. In the following sense, the one that do not form a bare category, you know, very thin, which is surprising. I have been reminded that by a logician that told me, how is that possible? And also contrasting the common notion that the other ones, the ones that behave humanely, are the generic case. Yeah, they're not. They're just the opposite. But so is the world. It doesn't matter that you put critical points or not. Even if vector fields without critical points are dense in the bare sense. Okay, enough. As I say, in the analytic category, that's the C omega, locally integrable, involutive implies locally integrable, which is the Cauchy-Kowalewska theorem, essentially. You can always solve if, I mean, except, of course, well, involutive. You have to have a non-degeneracy. Okay, that's one generality. Now, a small, you have classes, so let's have a small taxonomy. What do we know? It's the usual thing with PDE, and it reflects PDE. The structure is real if V is equal to its bar. So it means it is generated around every point by real vector fields. There is no problem about integrability because we have the Frobenius theorem. Remember, the fact that they span V and V has constant rank means that you don't have critical points where things go. It's regular. It's a bundle, a vector bundle. CR structure, that's a more modern notion. I think it didn't exist when I started, which is half a century or more ago. That's when V and its complex conjugate intersects only at 0. And they have become a great topic of research because if you take a submanifold, a real submanifold of Cn, which has the property that the rank of the tangential Cauchy-Riemann equation is constant, that's called the generic submanifold of Cn. That's the prototype of a CR structure. CR stands for Cauchy-Riemann. Rossi gave the first example on the sphere, three-sphere, of something that's absolutely not integrable. Elliptic structure, those are the best. You cannot be happier with any structure than you are. That means the V and V bar span everything, but they may have an overlap. The overlap is the real part. And complex structure is elliptic, so a real structure is elliptic if and only if you get the whole. Well, I mean, think of the definition. It's real, so V equals V bar. And V plus V bar has to be the whole complex tangent, so V has to be the whole complex. So that's real. Complex structure is the other extreme. It's a direct sum now. The overlap is 0, but you get everything. For that, all the problems for elliptic structure, all the problems which are purely local, I will discuss. They are totally known. You imagine, elliptic, you have vector fields, you form naturally the Laplacian, and you get lots of property. Not only that, there is a Neumann problem for the structure. It has been completely studied. So you have t variable, the real variable. You have z variable, the complex variable. And from the point of view of free complex variable, you have pseudo-convexity. And for the real thing, everything goes well because you have the RAM theorems, etc. So everything is known, and I will personally, in this talk, concentrate on the non-elliptic. So in an elliptic structure, every solution is infinity because you form the Laplacian. Okay. Now, local representation, I don't want to spend too much time, but you have, in the local integrability condition, you have some function which has solution, but they have furthermore the property that their differential spans completely the orthogonal. Okay? So they are all killed by the LJ, but the differential span everything. So you can make a linear transformation, a linear, complex linear transformation of the z's, substitution, and you can arrange so the real parts are already linearly independent. Okay, and that's local, huh? Strictly local. Let's not talk about global thing here. So that's nothing. It's a complex matrix. You can push the thing a little bit further. Of course, then you take the real part of the first integrals as coordinates. And they are because of the condition of linear independence. So you can write the first integral of that type, x plus I phi. Everything is a vector there. Because you have taken the real as coordinate. At that point, because you have the x in the real part, that allows you to make not linear transformation, but biolomorphic transformation of the z. And that allows you to kill all the monomial with x up to a finite point. Huh? Okay. So you can always assume that the imaginary part, that will be useful. I should be precise. What will be useful is essentially that they vanish quadratically. It's enough. But you can push that further. I am talking about a topic that, contrary to the topics of the lectures I have heard so far, there is no historical substratum. I mean, yes, for elliptic there is, but beside that, I don't have many ancestors to quote. The thing was born about the time when I, as a mathematician, were born, as a mathematician. Okay. Now, it turns out that if you use the first integral and the real part as coordinates, you can arrange for a basis of those vector fields you are interested in to have an extremely simple form. They start with d over dtg, then you have the derivative there, and you have those mk. They're not very complicated. The entries of the mk's, they are the Jacobian determinant of, matrix, the Jacobian matrix of the z's with respect to the x's. The x's are the real thing. So you have the Kronecker index. You see in the middle, this equation, this one here, you have all the properties. And that implies, namely, they are either 0 or they are the Kronecker index, which means that they commute, they all commute. You can have a group, not a group, a set of vector field that's locally, that span V, together with the M, they span the whole complexified tangent bundle over that local, and they commute. So that's, life is very simple. It's all at that kind of level until you start trying to prove difficult theorem. Well, then that becomes more difficult. Okay, let me go on. Okay, now that's the local representation of the differential complex. Here I define the topic of this talk. You can use the forms only in the dt's. Remember, we are in a situation, let me insist on that, of local coordinates T1, I think I call it N, and X1, Xn. These are in a certain sense intrinsic because they are the real parts of first integral that you have chosen. These, of course, are only required to complement the system of coordinates. You miss a certain number of coordinates, n of them, and those variables. So that's a bit arbitrary, the choice. I mean, it's local coordinates, you can change. But not the z's. If you change the z's, it has to be biolomorphically. Okay, in the z's, that means an invertible transformation. So in that case, you can consider those forms. Those forms. Those are Q forms. The dTi is the usual exterior product. And L, which is the action, the differential, like D in the RAM complex or D bar in the complex, are simply those. You see, you act only in the dt. Okay, here I should mention that there is a trick that I was very surprised to be the first one to use it in complex variable. As I learned by the book of Enkin and his collaborator, whose name I don't remember. Since they commute, you have L square equals 0. L from one Q form to the Q plus 1 form, then if you go further, it's 0. That's what defines the differential complex. Okay? I forget that. The trick is the following. Well, no, that's a differential complex about which I will talk. Notice the sol infinity of omega. I have to say one word about that. Those are the solutions that are smooth. But, you know, we're talking about cohomology here. I could have started with the solution that are distributions. I mean, as generalized as I want, then the forms become what's called currents. But the whole thing, from the cohomological viewpoint, is the same. I mean, it's, I like to talk about the infinity. I feel comfortable. I feel even more comfortable with analytics, the omega, but that's not possible. Okay, now here is an example. So, in the classical case, elliptic, the complex is locally exact. You have the global information by solving the Newman problem, etc., etc. But as soon as you go to CR, new phenomena appear. You lose local exactness. It's well known in this non-degenerate. Look at, this is a hyperquadric. And it's known that for certain values of P, you have solvability in the corresponding dimension. I think that's called condition ZPQ. It's an old stuff. And you have no exactness in certain dimensions. All right. I don't think I'm seeing it. A trick, yeah, the trick I was alluding to, it's to, instead of looking at the forms only in dTi, you throw in all the differentials of the first integrals. Now, that becomes almost intrinsic. The only, because the DZs, if you change them, you get a determinant which is analytic in those Z's. So the only non-intrinsic is the dt part. However, when you look at it, you see that it's really, you're dealing with a subcomplex of the RAM complex. And that's also true in complex variable, incidentally, or in CR. So you can do that. All right. Okay, that's a novelty, the first theorem. You have to understand that we are in an extremely primitive situation. We know almost nothing about it. I'm not talking about the elliptic, but the non-elliptic. Well, it happens that we can still state certain things if we are willing to do it as approximation. Every solution is the limit, every solution is the limit of such an integral or duality bracket. I put a cutoff function, because the key of y, I put a cutoff function so I can say that it works for distribution. But if you're looking at continuous functions, you just limit the domain of integration. That is absolutely universal. Whenever you have an integrable system, you have that formula is valid. That formula, incidentally, for harmonic analysts, there are people, some are my students, some not are my students, who have proved the validity of the formula for all the reasonable spaces that you encounter. The trouble left, that's immediate. But also the more sophisticated space, hardly, whatever. It works for all. I mean, I could not offhand mention one thing where it doesn't work. Of course, within reason. Okay. Even works for hyperfunction. I would say that it's a little delicate point, because we are not on an analytic manifold. We are on a C-infinity manifold, but still they are hyperfunction, and I will explain that in a moment. So that's what the statement down there. All right, here are the consequences. Let me go back a moment to the formula. Notice the formula. The integration, it's on dz, but dz at 0, at time 0. And dz at time 0 is essentially x. Essentially, not quite. So, if your solution, h of y 0, is 0, then it is 0 in a full neighborhood of the point, because of the formula. Okay, so the first consequences is uniqueness in the Cauchy problem. For people in PD, that's always very important. Also, that generates special curves on the manifold, essentially transversal to the t equals 0. And those are very important. They're propagators. For instance, they're propagators of support. If one of those curves touches the support of the solution, it's contained in the support of the solution. That's what motivated my interest in the problem. It's only as a byproduct, because I discovered somehow that CR people were interested in polynomial approximation, that the second theorem there appears. Every solution is a limit of polynomials in the first integral. Okay? That has immediately a corollary where the z's are constant, all the solution is constant. That's a phenomena that did not exist, or at least was not on the foreground in the classical thing. It's true because in the Frobenius theorem, look at the first integral as the things that are constant on the orbits or the leaves of the foliation. Those are the first integral. And of course, the uniqueness holds and all that. But the lack of interest so far for the corollary is that a lot of attention has been concentrated on CR. And in CR, the sets on which they are constant are discrete. They are single points. CR function, therefore annihilated, say, by the tangential Cauchy-Riemann vector field, they are constant only on single points. Of course, they can discrete. So that notion was completely new. And it's in the motivation of my research on that. Don't think it's very young, though I'm very old, and there's little. Let's go on. Now, for the theorems, I need that. And I knew that from the beginning. I proved it. You have the same for forms. Let me state it clearly. You take a Q form, and you suppose that it's annihilated by L, that differential L, the differential standard one, okay? You apply L to an element, and you add a dt. Well, it's L close, but it is limit of exact LU nu, which furthermore have the property that they are entire functions of Z. We can even take them polynomials of Z, which we are talking about, okay? Polynomial coefficient. And I personally knew from the beginning, the proof is the same, essentially, as the one for solutions. So it's a modification of the Weierstrass approximation theorem, and it's the same. But this is fundamental in the proof of the theorem in the complex, because you produce solution of some equation, and you don't quite get it but you can correct it by the Mittag-Leffler. It's classical, the Mittag-Leffler. You get a series representation, the difference between saying it's a solution, then you can approximate, things like that. I need some water, I'm sorry. Okay, those are two fundamental facts. As some of my colleagues keep reminding me, the proofs are really elementary. They can be in a textbook for students. Actually, one of them is in a textbook by Eli Stein, which was a great honor that he put it there, namely the approximation formula. The approximation formula gives immediately the Levy theorem about when you can extend on the side of, say, a strongly pseudo-convex surface, you can approximate by polynomials, and therefore gives you an extension. And without minimal regularity, because you can do it for continuous. If you look at the book of Hermander, you need C4 on the surface. Here you continuous works. And the proof is much simpler and more natural. Okay. Yeah, about the approximate Poincaré lemma, it might not hold. Rosé gave an example where the distance to zero is fixed. It's 1, whatever metric you use, which is strange, he did that. It's in a CR situation, of course not embeddable, because if it's embeddable, you get the first integrals and you would contradict the approximate Poincaré lemma. So it's a curiosity, and all right. Now we come to the local topology of the fibers. In what I am going to do, that plays a crucial role. And in a certain sense, I will explain why it's unfortunate, but there is one evidence it's unfortunate. It's that CR, the fibers, the point where all the solutions are constant, are single points. So the homology of the fibers in that case is totally trivial, and therefore this doesn't contribute anything. Okay, so the condition PQ is the following. Many properties in mathematics are called P. I think Nirenberg and I were among the first to use the condition P, and that in that sense. So, in the sense of germs, you want that near a point, the homology, I'd say the singular homology, and say of every fiber, but it's enough to have them for the smooth fibers, is trivial. That means, let me point out, let me take Q equals 0. Q equals 0, that means connectedness. Okay, it says the following. You have one neighborhood, say, of the origin. You look at a smaller neighborhood, and there the fibers. Remember, those are the sets on which all solutions are constant. And you can have such a set that's easy to find. So these are the fibers. The condition says that they are connectable. If they are not connectable, then things go bad. Let me give an example where they are not connectable. That's always for q equals 0. You take this and this, but take the, I said take the smooth, take the hyperbolas. They are not connectable. That piece and that piece cannot be connected. You are not allowed to go far. So you take the big neighborhood, and then you take a smaller neighborhood, and there they are disconnected. And if it's small enough, that the sub-neighborhood, then they should be connectable. That's a typical example. One where they are connectable, I want to write. Both are, here again, the origin. Suppose that the fibers are circles around the origin, then trivially connectable. Okay, because you take any neighborhood smaller, you find a circle in there. The circle, and the circle, let me be nasty, let me suppose that the neighborhood has that form. They are disconnected, but they are connectable. Okay, that's the main idea here. All right. Well, I seem to have come back to that. Yes. What about the case of one vector field? We know everything about one vector field. And we know that the condition P is necessary and sufficient for local solvability. P0, that connected this thing. But that's not how condition P is known. I am not assuming that you are familiar with the topic, so I will explain what the... You take one vector field. Let's make life simple. Let's take a vector field in the plane. Well, you can reduce it very easily to this. Remember, the dt is at the beginning, but you did not have a purely imaginary coefficient, but here you can by rectifying the real part. So you can write that in terms of the first integral. The first integral is this. I don't want to write much, so you'll excuse me if... It appears that after some operation, this vector field, it's essential. In my slides, I have the exact computation, I think. Yeah, it's written there. But forget about that formula. Essentially, that formula says that you are dealing with this. It's false, of course, the way I'm stating it. But let me state, the correction is there, the exact correction. Of course, this is false. But essentially that. And condition P says this guy, therefore this guy, for x fixed, should never change sign. That's the condition necessary and sufficient for local solvability, which is local exactness at the bottom of the thing. If you look at this, which is, in a certain sense, the real thing, it's explained there, it means that d phi t has to be monotone. That has to be a monotone function of t. Okay, let me show an example where it's not. Here. T squared. It's not monotone. So here is the t variable. And look at the fibers. That means you fix x, okay, x0. You fix y, which happens to be fixing t. You fix it. Hey, hey. however close you come to the summit, it's disconnected. So no. These examples are very famous. They are Misoata, referred to Misoata. The other case is T cube, or T any odd number. Well, in that case, the graph, it's like that. This, and the fibers are single points. So we have connected the local exactness to the old solvability, and we forget about the old solvability. Now we fix our attention to the topology of the fibers. Now, let me say one thing. If you want to study this kind of stuff, the first thing you want to do is not to have an X. If you don't have an X, so the vector fields are of this type. Okay, there are more of them, of course, something like that. That's what's called a tube structure. Tube structure. Because of the Buchner tube theorem. Namely that in dx, you can go all the way, all of Rn, but not, of course, in T. Now, remember that for us, T is multivariable. It's not just one T. So you could ask, global in X allows you to make a Fourier transform. So you change your vector field to this vector field. This is known dtj plus I. I'm putting the bj t and cj. I should put, yeah, okay. And c, let me put c here. By Fourier transform. So the frequency appears. But that's an ordinary. You are in the RAM with an exponential. Okay, you have to make with the integral of bj tc, it's essentially the solution would be of that type. So it's very easy to see here when you can solve locally or not. And it reflects the topology of the fiber in any dimension. That's, I think, my first article in the Annals that was published thanks to the kindness of Eli. I give a complete description of the differential complex in there. There are two drawbacks, one very intrinsic and one artificial. The artificial one is that if you make a Fourier transform, you are talking about global things in X, which is natural if you have a tube in X, a tube on a. The first drawback is that you cannot say anything global about the T, because just imagine for a moment that the T vary on a torus. And then immediately you have number theoretical constraint and small divisors, all that stuff comes in. So that's one. But the global in X, it's also a limitation. Well, for technical reasons. I mean, it's easy to do, but for technical reasons. So what you always do that. The story for a single vector field started with the Misoata operators, which are these in the plane, two variables, x and t. They are these, and they are solvable if and only if k is an even integer. So that the integral is an odd integer, and you have fibers, single points, and not a couple of points, near zero. Okay, so that's that part of history. Okay, now in in the tube structure, you immediately come to the cohomological condition. And instead of looking at the topology of the fibers, you look at, you are forced, you have no choice, but to look at something like that. Dot product with C. I am in many dimensions in X, arbitrary dimension in X. And this, the in principle, what it says is the cohomology of this constant. Let me repeat, I am in the tube situation, which is the test field. So you have that constant, but there is a frequency here. So the topology of that set, it's in fact, what do we put, A, the topology of the superlevel or the sublevels. That's due to the Meyer-Vietoris theorem that says that the information on those two sets give you the information on the cohomology or homology, whatever you want to use, of the boundary. So people like me or some of my students, they just look at superlevels and sublevels. And that you do also when there is an X, but things get much harder. Okay. How am I doing time-wise? I have no idea.
8 minutes.
How much?
8 minutes.
Okay, fine. I think that would do it. Okay. Where am I? No, tube structure. Okay, that's one case where the work can be done completely. You suppose there is only one Z. And I will explain within those 8 minutes or 7 why that's such a crucial thing, one Z. So you have one Z, one X, lots of T's. So you have lots of vector fields. They are in T, and you have that X. In a certain sense, if you want to look at the elliptic structure corresponding to this can be decomposed in the Durham complex plus the D bar Z complex. That's the elliptic thing. And somehow you embed, I'm using a bit the words unprecisely, your structure into a bigger, the complex structure. This distinction plays an important role. And let me point out to a crucial thing. If you have only one Z, you have the Z in the plane. In the plane, every domain, every open set is a domain of holomorphy. And that saves you, allows you to solve D-bar equation, which you need for correction in the general case. So I think it's in 83. Yeah, we are at the history, we're at the page before the last. In 83, I published an article, it's in the AXA, where I conjecture that the condition P in dimension or in degree Q minus 1 is necessary and sufficient for local exactness. I was only able to prove it at the lowest level, at Q equals 1, and under the hypothesis that the whole structure is analytic, and the proof is technical. You integrate and correct and all that. Okay. Now, that's history, pure history. I will finish with it. In 83, well, it's my article. In 1990, two of my students, Cordaro and Hooney, proved the conjecture on top level. That's the very undetermined system. It's a divergent system. So you have Lj, Uj, you want to solve that. So that was that. Then apparently in 1991, there is an article by Cordaro and myself, of which I have no recollection whatsoever, but I found it in the references, where apparently we proved that the condition is necessary in the C-infinity case. I have the impression that something happened there. Anyway, certainly something happened here. So, more importantly is the article with Gerardo Mendoza of 91, when we prove that it's sufficient provided you have it in degree q minus 1 and q minus 2. The interest of that, it's not in the statement, of course, but it's in the technique. The technique uses the technique of my paper in the annals of before. You subdivide everything into cubes whose size, say diameter or whatever, whose size it's proportional to the inverse of the frequency. And then you count how many cubes. And you get an estimate with an horrific loss of coordinates, depending on the number of those cubes. But you have the Mittag-Leffler operation, and that saves it. Okay, so that's what we use with some more tricks. I'm going very brief on that. And we come towards the end. Oh, I want to say a word about that. With Cordaro, and that I remember very well, we use old concept of Leray about sheaf theory, and using those we were able to prove that the condition is necessary and sufficient provided we are talking about solutions that are hyperfunction. And then there is the question, how come they are hyperfunction? We are in C infinity. Yes, but we have the Z's. And the Z's add a structure. You can use them to transfer things from the complex space locally to the manifold. And you define the hyperfunction as boundary value of holomorphic function going to the boundary of something at arbitrary rate. And you have to make cohomology classes, whatever, but it goes perfectly well. In fact, it indicates that there is a structure below the concept of local integrable, which I've called hypoanalytic. Namely, you have Z's all over. You ask that on overlap, they are biholomorphically equivalent. And incidentally, there might be many different ones, but they are those structures where there's only one, and those I call the hypocomplex. And they contain many interesting examples. Okay, but anyway, Cianillo and myself prove the conjecture under the analyticity condition. It's a horrible article. It's a horrible article. It was considered by the ACTA for 6 months. They put me in touch with the referee. The referee knew each other very well. We were friends. And it almost ended up with a nervous breakdown of the referee because he had several real correct objections and then some absurd ones. And the paper was accepted by Tao, I think, in the other journal. Anyway, it had one thing. We proved the theorem on the lowest eigenvalue of the Laplace-Beltrami operator on compact analytic manifold that tend to a variety, to a thing irregular. We have proved we needed it, that the lowest eigenvalue of the Laplace-Beltrami operator goes to 0, but not faster than a certain power of the inverse of the distance to the singular set. And apparently it was not known. It had been proved by Gromov for polynomials, but we don't know its proof. We just prove it for analytic function. Okay. It was very complicated. It's a proof I am not proud of, but then my 2 students prove it with a very elegant proof where they use harmonic analysis. That's the latest connection with this. They have dyadic decomposition. They have a nice trick, which we missed in the article with the first one, with with Mendoza, with Gerardo Mendoza. You look at sub-level, and you make all the subdivision in little squares. And they had one idea. We talk about the sub-level for the value A of the whatever, the fibers. They went a little bit down by epsilon. Then they construct something which was horrible at the boundary, but they took the restriction to something that's more inside, and it worked. With some harmonic analysis which was beyond my capacity, certainly not my collaborator. Okay, now last page, just last page. Okay, so the conjecture is proved. In core 1, the homology of the fiber is necessary and sufficient for the local exactness. Well, what do you do next? So this mathematics had not much of a past, just compared to the background, the substrata of what we have heard. Here is practically nothing. I mean, there's Nirenberg and me and Ormander, nothing. The present is not very brilliant, 1z. Who really cares? You want something more general. Well, we don't know, because we use so much the fact that every open subset of C is a domain of holomorphy. What we know is that when we try to generalize, which we did at various times, you encounter the problem, the eternal problem in complex variable, is the range of D bar closed or not? But we don't even know how geometrically it fits with the whole thing. But there is a totally different approach possible that will not give you a result. It's associated with the name of Treves. It's one of the most beautiful theorems. I know it uses quantized transformation. It transforms whatever operator you are dealing of that type into D over dz1, D over dzn, but in a strange set. And one is, you want to solve, well, actually in the case of Treves, it's one vector field, it's D over dz, but dz1, sorry. You are in several variables. You have the boundary of a set. Can you solve it in hyperfunction on the boundary? And there, P, the condition P, it's necessary and sufficient that the set be strongly pseudo-complex, which is a fantastic discovery, which links completely complex variables. Now there is an approach like that for several vector fields, because you want a conjecture. That result does not give you local solvability, but it tells you what the proper key property is. And I would like to know what is, when I have two z's, what is the thing? Okay, let me stop.